Hey guys, today we're going to do 7.2 properties of exponential functions. So you will be able to explore the properties of the functions of the form y equals a times b to the x power, and you will be able to graph exponential functions that have base e. Our essential understanding is the factor a in y is equal to a times b to the x power can stretch or compress and possibly reflect the graph of the parent function y is equal to b to the x power. Here we have the graphs of y is equal to 2 to the x power in red and y is equal to 3 times 2 to the x power in blue. So each y value of y is equal to 3 times 2 to the x power is 3 times the corresponding y value of the parent function y is equal to 2 to the x power, which we see in our graph. So what's that saying is that y is equal to 3 times 2 to the x power stretches the parent function of the graph by a factor of 3. So how does the graph of y is equal to negative 1/3 times 3 to the x power compared to the graph of the parent function? So step 1, we are going to make a table of values. For x, we're going to have y is equal to our parent function, which is 3 to the x, and y is equal to negative 1/3 times 3 to the x. We can do negative 2, negative 1, 0, 1, and 2 to plug in. So when we plug in negative 2, we get 1 over 9. We get 1 over 3, 1, 3, and 9. And we get negative 1 over 27, negative 9. I'm sorry, negative 1 over 9. Negative 1/3, negative 1, and negative 3. So if we're to graph those functions, I'm going to do our parent function in green. So I have negative 2, 1/9, 1, 1/3, 0, 1, 2, 3, 1, 2, and then 2, 9. So that's what my parent function looks like. Then the transformed function would be negative 2, negative 127, negative 1, negative 1/9, 0, negative 1/3, negative 1, negative 1, and 2, negative 3. So here we reflected over the x-axis and we vertically shrunk. So it's a vertical shrink. So a horizontal shift is y is equal to a times b to the x minus h, which is the same as the vertical stretch or compression. Y is equal to parentheses a times b minus h times b to the x power. So if we're adding or subtracting in our exponent, we have to think about as horizontal shift. and a vertical shift was on the outside. So on the outside would be a vertical shift. When we are moving our graph up and down or vertically, we are also going to be moving our horizontal asymptote. So our horizontal asymptote will not always be at y equals 0 or our x-axis. It's going to be at y equals k. So how does the graph of each function compare to the graph of the parent function? We have y is equal to 2 to the power of x minus 4. Since we're on the inside, this is a horizontal shift. And we are shifting 4 to the right. We have to remember the right because horizontal is left and right, which is opposite on the inside. So just a summary, if a, the absolute value of a is greater than 1, we stretch. Absolute value of a is a decimal or a fraction, we shrink. And if it's negative, we have a reflection across the x-axis. Then we have our translations in our exponent left or right. And then k, which would be outside of our function, is up and down. So we can use an exponential model in life. So the best temperature to brew coffee is between 195 degrees Fahrenheit and 205 degrees. Coffee is cool enough to drink at 185 degrees Fahrenheit. The table shows temperature readings from a sample cup of coffee. How long does it take for a cup of coffee to be cool enough to drink? Use an exponential model. So we have our table. We have x, which is time, y, which is temperature. We know our set of values and we know the best serving temperature. We need to know the time it takes for a cup of coffee to become cool enough to drink. We have to use an exponential model to find the time it takes for coffee to reach 185 degrees. So we can use our calculators for this. So we would plot our table, our data into our table, and determine if an exponential model is realistic. We can determine this because we see our data points going down in an exponential way. The graphing calculator exponential model assumes the y asymptote is y is equal to 0. So since room temperature is about 65 degrees, we're going to subtract 65 from each temperature to calculate this third list, so that we would think that the, because in our first set of data, our y-intercept was 68 because that's room temperature, but really our calculator wants to think our asymptote is 0, so we have to change that. Then we use what we used to use was linreg, then quadreg. Now we're going to use expreg because we're going to find the exponential regression for L1 and L3 because L3 was our new list. And we're going to move our equation, which we get from our data, with A, B, and R, to move it up 68 to find out how long it takes. So we're going to plug this into our y equals, find the table, and we want to find how long it takes the coffee to get to 185. So we find 185, which is 3.1. Meaning the coffee takes about 3.1 minutes to cool to 85 degrees. Up to this point, we have worked with rational bases, and however, we also can have exponential functions with an irrational base. So one very important irrational base is the number e, and the graph of y is equal to 1 plus 1 over x to the x power has an asymptote at y equals e, or y is about 2.71828. So this is the line E, and this is the equation where the asymptote is at y is equal to e. The natural base exponential functions are exponential functions with base e. So these functions are useful for describing continuous growth or decay. Exponential functions with base e have the same properties as other exponential functions. We can use a graphing calculator to evaluate that e. There's actually a button that is e on our calculator to give us the value. We can graph and then find what y is equal to at x equals 3, or we can use the table. So e to the third power is about 20.086. In lesson 7.1, we studied interest that was compounded annually. The formula for continuously compounded, we use the number e. So our new equation is going to be a of t is equal to p e to the rt, where p is our principal or our initial amount. A of t is still our amount in account at time t. T is time in years, and r is our interest rate annually. Suppose you have won a contest at the start of 5th grade that deposited $3,000 in an account that pays 5% annual interest compounded continuously. Since it says compounded continuously, we have to remember a of t is equal to p e r t. How much will you have in the account when you enter high school 4 years later? So we are going to take our amount after 4 years, which is equal to 3,000 times e to the r. Our rate isn't 5, it is 0.05 times t, which is 4. We put this into our calculator, and our amount after 4 years is equal to $3,664, since we are rounding to the nearest dollar. And that's all.